Okay, so welcome back, everyone. Just a quick organizational issue I was asking in the break. Sometimes people also like to look ahead and prepare for the lecture, which is something I, of course, want to very much encourage. I don't have a concrete schedule online about what I will discuss then next time. But I have on the website now the schedule shows you the topic of each lecture. And like I said, I sometimes will make changes, but the next one should always be up to date. And if you go to the website from last year, you see which chapters of the book that covers and what you can also already access the slides from last year. So if you want to prepare, just go there. I can also put a link directly on the lecture site later so you can access it directly. If not, there is a link to last year's material on the very first page from the website at the bottom. The reason why I'm not putting a schedule online concretely is that I always try to improve the course every year a little bit, which means that I might make last minute changes at the very last moment, which is why I want to keep a certain flexibility and not put too much concretely online now, but it should not be changing that much from last year. So if you want to use it for preparation, you're well welcome to look at at the schedule from last year. I was also told that there is a wrong link to the old computer science site. I will try to find that and fix that. So be careful if you look at rooms or times and come to the old computer science page with the white table there. Be careful, you might end up in the wrong year. I will try to fix that. Good. All right. So the remainder of today we'll just talk about a little bit about the basic methods of image generation for computer graphics. So just to give you a little bit an overview and make you familiar with the terminology, because you will hopefully start with the practical soon. So you should start, but of course I don't know when you will start. This can be, like I said, a little bit overwhelming at first, especially if you don't have experience at all. Will it make it? Let's hope. Anyway, so this will be a very high level, and don't be confused if I tell you a lot of technical terms now that you don't understand. We will talk about this later in the course, and some of it we'll also do in the practical. So it should work out, but it makes sense to make yourself familiar with the terminology. That's why I'm giving this short overview today. Good. So I said we will not talk about animation, but we will mostly dealing with modeling and rendering, and mostly with rendering and a little bit about modeling. Modeling is roughly said, so this is not a formal definition here, but just intuitively, modeling is basically creating a 3D virtual world, and rendering is then creating a 2D image based on this 3D world, which is a mathematical abstract description of a 3D world or a 3D scene, and then putting that abstract 3D description onto a concrete image, which is basically a matrix of single. It's very distracting because I always see the light changing here, so I don't know if it goes out or not. Anyway, so which is basically a matrix of an array of single pixels on your screen, and we have to then decide what color we give each pixel on the screen based on this 3D model. And there are two basic approaches that I used in graphics. One of them is ray tracing, the other is projective methods. And when I saw this, I realized there was a problem, obviously, with my Dropbox account, because I made the slides on my computer in the office, and apparently it didn't get synchronized. So I have to switch the order now, because I want to first talk about ray tracing and then about projective methods. So you see, I like to make last-minute changes. So what we want to do is we want to create an image of the world. And like I said, we have to first think about how does the world look like. If we want to draw a pixel on the screen, we have to know what kind of object do we have to draw on that pixel, but also how does that object look like in this particular scene. Because if, like I said already, every time we look at something and we see something, there is some light involved. If there wouldn't be any light, we wouldn't see anything. Everything would be dark. So there has to be some light source somewhere that gives us light, that makes us see this object. So there is a light source and that light source shines in a certain direction. And then, for example, there might be an object here, like a glass, and then that light is reflected to another object, and then that light is again reflected to another object, and from there it is reflected towards the screen or towards our eye where we look at the object. And then we see, so then we know at this point we have to draw the pixel based on this object, based on the light that is reflected from here, based on the light that is reflected from here, based on the light that is reflected from here. And this is exactly what ray tracing does. Ray tracing is a technique where we trace the ray of light, but trace it in the opposite direction, because we say we have a screen and we want to know what kind of color do we have to give this pixel here or this pixel here. So we look, when we look into that direction, the object that we see here is the direct extension of this ray that we draw from our eye to the pixel. And then if we continue, we see this is the first object that we hit. So if it is not a transparent object, this is the object that we see. If it is a transparent object, then we also, of course, see the object behind it. But if it is not, then we just see this object. So what we see or what we have to draw on this pixel only depends on the color this dot of this object in our virtual world has. And this color, and this is the part where the physics come in. From physics, we know if we have a light source that shines in a certain direction, hits a spot, it gets reflected with a certain angle, and the light that we then see at this here depends, of course, on the angle that the light hits, on the angle that it gets reflected, but it also depends, of course, on the surface of the light, on the color, on the surface of the object. On if it's red or green, we see it differently. If it has a different structure, if it is wood or metal, we see it differently. So these are all the kind of factors that that are considered. But also importantly, it depends on the light that reflects here. So if we follow this ray here, and then we see, okay, it depends on the light that is reflected here, which in turn depends on the light that is reflected here, which in turn depends on the light that is reflected here, then we can calculate the value for this pixel. And this is done for every pixel, and this is then the technique that is called ray tracing, where we basically follow a ray of light for each pixel that we are drawing on the screen. Which is also why this produces very realistic, very good images, because you see here that we're really considering, for each single pixel, we're considering all possible light sources. So for example, if this is a transparent object, then we do not only consider the light that comes from the reflection, but also transparent objects also leave light through them. So if you look through a glass, you see that it is you see the light also through the glass. So we also follow it here. And if we have then another light source here, oh, it's very badly drawn light source, but you get the idea. Then of course this also adds to how we see the color here at this pixel. Also, if we, for example, have a different kind of glass, the light might be not go straightly through it, but it might get a little distorted. So if we have a different kind of glass here, the light might be moving there at a different angle. So it doesn't... This is our glass, and this is how the light would go through directly. But if, for example, the light gets distorted by the glass, then it goes through here. So if we have a light source here, in that case, it will look differently. And this is all automatically considered in ray tracing, which is why ray tracing produces very realistic images, because it considers, the approach considers all kind of lights. It recursively processes all kind of possible rays that could influence how we see the color at this particular point that is then represented by the pixel on the screen. But that is also why it is very, very slow. Of course, there are approaches to improve ray tracing and make it real time, but in general, ray tracing is a quite slow approach. But this is what we actually were doing in. So these are some examples from ray tracing, and you see that these are very realistic images. So this is an office scene, and it's really hard to distinguish that from really an actual photo. because you see all the lighting and everything is considered. The only thing that makes this distinguishable from a real scene is probably that it looks too perfect. It's too shiny, like dirt or stuff. This is something, of course, that is often very hard to simulate with ray tracing. A lot of characteristic of ray tracing is that the images look very good and very realistic, but at some point also too realistic, too shiny, and too perfect. Good, yeah, and in previous years, so like I said, these are the old slides. Forget about it. It should be 2 years ago. Till 2 years ago, we used ray tracing also in the practicals. People had to implement a ray tracer, and these are some of the nice results that they have. So you see, these are really kind of nice and interesting images. But then last year we switched to shader programming, and the reason was the redesign of the of the bachelor curriculum to the new gaming technology bachelor. Sorry. Which is exactly for the reason that ray tracing is, on the one hand, it gives very good quality results, but it is very slow, which is why it's usually not used for game programming or for all kind of interactive applications, because then you need real-time interaction, so you need to change the graphics very quickly in real time, which is not possible with ray tracing, which is why for that we usually use so-called projective approaches, and from the programming side, shader programming, which is what you will do in the practicals. So now I have to go back because I switched the slides. Here we go, projective methods. Let's make sure I don't forget anything. Yeah. So, like I said, for ray tracing, we basically go through it pixel by pixel and then recursively consider all light condition. So ray tracing is basically a pixel-based approach where we go through each single pixel here, and then for all the pixels here, we consider them. For projective methods, we say we do not look at the individual pixels, but we look at the individual objects. So projective methods are object-based. So if we have, for example, 3 objects here, like 3 triangles, we look at each single object and then project it towards the screen and then draw it on the screen. So in the end, we also end up having 3 triangles here, but we get them not by going through all pixels and thinking about what should we draw this pixel, but what we go through all the objects and say these are all the objects I have in the scene, so this is what I want to draw on the screen, which of course is more efficient if you only take 3 triangles. Of course, if you have more, it also becomes more complicated, but also you see here that in contrast to ray tracing, which is a recursive approach where for each pixel we go through a loop and consider all different light influences, and in the worst case, of course, this light stream that we are following can be reflected from all objects that we have in the scene, which makes it very inefficient then to calculate it, or makes it much slower, whereas here we just go through the number of objects once and then project them on the screen. But of course you also see that because we're not recursively following the ray, that we have to consider each light source individually, and if we don't consider it in a recursive way that we consider all reflecting influences as well, the quality of our images isn't as good, which is of course why often if you look, for example, at ray tracing images and the images that you have in your computer games, or if you compare, for example, a Pixar movie with the related computer game that you have for the movie, often the graphics in a computer game look much less impressive, but that's because they are real time, they have to be done immediately, which is why we have to use techniques that are not as sophisticated and not take as long as the ones that are used to make the movie, because then they have time to spend on each individual frame, because you just have to render it once, whereas and then later you watch the movie, but in a game you immediately want to have the reaction there when you interact with it. This is why projective methods often don't look that good, but they are faster, which is why why they are mostly used for computer graphics in all kind of interactive applications. And this is what we will do to this time now in the practicals. We will use shader languages. I'll say about this later. And of course, when you look at this simple example here with 3 triangles or the number of pixels here, it's obvious that the 3 triangles is more efficient because it's just 3 triangles. But if you think about The model I had we saw at the beginning in these photos from Pixar, where we saw this from Monsters movie, where you have like hundreds or thousands of triangles for just one character. Then of course this is also not very efficient, but the advantage of these projective methods is that they are supported by hardware. So and if it's supported by hardware, it usually means it's very fast. So we have hardware support, and this is exactly what you do with shader programming. Shader programming is basically a special API, special library, special functions that allow you to program directly on the graphics GPU that you have in your computer, the graphics processor. So which is why they are very fast, and which is why they're very suitable for interactive active applications like games. Yeah. Good. Now, all right, yeah, now that's the slide that is missing because I have the old version here. But fortunately, I also have a movie. So I just want to, you've seen the results from the previous year from the practicals, and this is now just a quick. Wait, do this here. Oh no, that's too much. Just a quick some examples from last year from the practicals. This was from the third assignment where they used different graphic techniques to do different kind of effects with this head here. So we can just quickly scroll through some of them. Yeah, that's quite nice. Let's see. Yeah, so this is this blurring effect. Oh, that's a pretty cool one. Oh, that was also nice. Yeah, that's also nice. All right, yeah, so you see a couple of examples. And if you're not impressed by them, that's even better because then you should be very motivated to make something better this year. So next year, hopefully I can show your results here. Good, so let me see. Okay, that should fit again now with the slides. Yeah, sorry, I kind of screwed that up with the version, but I will put the new version and the old one online, but it's shouldn't be much of a difference. Good, yeah. So just a few more closing words on the a quick and rough overview of the procedure, just to make you familiar with the terminology and the basic steps. We will talk about all the details later, and you will see them in the practicals, but that's the reason why I want to mention it at least once here, that you don't feel like completely lost when you look at the practicals and you don't see a lot of new terms that you don't really understand. So one of the terms that you often see when you talk about computer graphics, especially in computer graphics programming, is so-called graphics pipeline, which is basically a very abstract concept or term to describe a more abstract concept, although there are of course very concrete implementations or realizations of it. So for example, sometimes pipeline is used to describe actually the hardware realization of the graphics, because you have certain, in a graphics processor, you have certain functions that are optimized for graphics, which is why the graphics pipeline is sometimes used to describe this. But it can also describe a software implementation of it, or sometimes graphics pipeline is also used just to describe the higher level concept of it. But what is all together with this is this notion of a pipeline. So just a few words about that, why we use the word pipeline, or what pipeline means in general in computer science. When we speak of a pipeline, we usually use it to describe a procedure that involves several steps, and the output of one step is always the input for the next step. And this is also why it is used very much in parallelization. So if you have parallel multiple processor machines, then you often use pipeline processing. And the reason for this is it's pretty simple to understand with a simple example. If you have, for example, 3 data units, A, B, and C, and you want to process them in a pipeline with 4 steps, then you start with A in the first step. Then the second step, you do the processing from the second step, then from the third step, and then from the fourth one, and then you have data unit, the processed one, let's call it A dash, after 4 steps. Then you start with processing B in the 5th step, 6th step, and so on till 6, 7, 8. Then you have B dash, so you have A after 4, B after 8 steps. And then in the 9th step, you start processing C, step 10, step 11, step 12. So after 12 steps, you have all your data processed. Now, if you think about it, if you have a multiprocessor machine, if you have 4 processors, then you could calculate each step on an individual processor. So you could start with A. Let's say this is processor 1, processor 2, processor 3, processor 4. You start with A here, then you go to the second step, but since that is done on a second processor, you can start with B already here while you're at the second step of A on that processor. And then, of course, in the third step, you can use that processor to process B. And in the fourth step, you're done. You have A dash again in 4 steps. But while you're doing this, you can already process these here. So by the 5th step, you already have B dash. And by the 6th step, then of course you have C. So you have all your processing done in half the time. So obviously this is faster, and it's clear why this is faster, because we can process them parallel, and we can process them parallel because of the structure of a pipeline. And this is why when you study parallel processing, you often hear the term pipeline, or you use the parallel processing to explain the notion of the concept of a pipeline, which is what I did now. Of course, in graphics, we also use often parallel machines or parallel processing because we want to speed it up. And like I said, graphics is very slow, and if we want to have real-time speed is a really big issue. But in general, pipeline is used in graphics to describe this high-level concept of having several steps that we have to go through, from, in graphics, a 3D representation, an abstract 3D representation, to a concrete 2D visualization on our screen, which is also from 3D models to 2D pixels. Good, yeah. So, and you see here also why this definition is a little vague. I looked up in the book how they describe or define a graphics pipeline, and you see these two kind of definitions. One is at the beginning of the book, the other is in the chapter about graphics pipelines. And you see even there the definition or the description of it is rather vague, because it is like a term that is more vaguely describing a concept. Good. Yeah. So I said we are. The graphics pipeline describes the procedure or the steps from the 3D model to the 2D visualization on the screen. So if we use the pipeline in an application, we first start, of course, with the 3D geometry. So we have a 3D here, and we move that, or we process that to get a 2D on a display. So the 3D is the model, not the application. The application controls everything. So to do this, we need certain operations that are done as part of this process, and these are usually this set of operations is usually called a graphics API. Graphics API. So API stands for Application Program Interface, and yeah, this is the part where I usually then remind the people that we have people with very different knowledge levels here. So I'm pretty sure people are sitting here and thinking, oh my God, he's explaining what API stands for. What kind of basic and simple stuff is that? But I'm pretty sure there are also a couple of people who, if I would just say API and not explain what it means, who would like, what the hell is going on here? I have no clue what he's talking about. So yeah, you see the problem here. Just be aware of it. That if you get bored or if you get too far ahead, it is I have to find a decent balance here. But of course, if you are at any time feel lost or so, let me know. Then I try to explain it in more detail. If you feel not challenged enough, contact your teaching assistants, and they will give you some graphics assignments for the practicals that will challenge you. I'm pretty sure. Good. Yeah. So graphics application program interface is basically a library or a set of functions that are optimized for a certain task or for certain domain, and a graphics API obviously is an API that is optimized for graphics. So if you go to books or the practicals, you will see that you will see this term very often, graphics API, and common graphics APIs are OpenGL, and that's the open source for Linux and also I think on Mac, and for Windows we have DirectX, or actually Direct 3D is the 3D part of DirectX. DirectX is more a general multimedia library or API, and 3D then is the 3D sub part of it. And then there are also so-called shader languages. Which is for OpenGL. Make sure that I don't make a mistake here. GLSL. And for Microsoft it's HLSL, and this is the one you will use in the practicals, and this is just a more like the it's kind of in the middle between the OpenGL and DirectX is more on the basic level where they directly program the hardware, whereas the HLSL, the shader language, give you more flexibility to program the hardware to do more advanced things with it. Yeah, like I said, I mean these libraries are based on the hardware, but there are of course also software implementations of pipelines. For example, the most popular I think software pipeline is RenderMan, which is a software from Pixar that they also use to make their movies. And of course, the reason is if you have a software pipeline, you are much more flexible because you do not have to rely on the actual processor structure. If you have a hardware library API, you have to stick to what the hardware allows you to do, whereas with software you're free to do everything. But of course, software is usually slower when you don't have hardware support, which is why it's obvious that Pixar uses them, because speed is important for them, but not that important because they're making movies and not interactive applications. But if you want to program interactive games where speed is an important issue, then of course the hardware support is more important, which is why we're doing this. Why we decide to switch to the shader programming. Good. So these are the kind of operations that you use for that. But then also, of course, you want to do these operations with a certain geometry. And if we have a hardware supported library, then of course we are also restricted by what the hardware supports, and this is usually or sometimes described with the term primitives. So primitives are basically the subject of the subset of the geometry that can be handled by the API that you're using. Good. Yeah, so like I said, just a few terminologies to make you a little bit familiar with them, to make it easier for you when you read all the stuff with the practicals. So we expect that also you get a little bit active. I will not tell you everything about the practicals. There will be some 2 introduction talks here from the teaching assistants for the second and the third assignment, but in general for the practicals we expect you that you also make yourself that you get active and read the stuff yourself and look around also on the web. There is a lot of information. I will post more detailed, more links to references online on the website also later. I mean, this is an important thing that you also have to be aware of, that with a course like this, I can only give you a very rough overview of the things, but there are a lot of things involved that you really have to get active yourself. So if you really want to learn good graphics programming, you have to look into the material yourself. You have to learn how to look up references and stuff, and this is something we want to also encourage you for the practicals. Good. Yeah, so just a few more words on the procedure that is going on. Like I said, we start with, we want to project the 3D model on a 2D screen and then do some color, put some color on it, which is a process called shading. So first of all, we have to transform, of course, the 3D geometry to a 2D geometry on the screen. And we do this by a process called perspective projection, because we project the 3D model on the 2D screen by considering the perspective that we have. So if we have the same triangle, but at a position that is further away, obviously it looks smaller to us. So we have to consider this perspective, and this is done in a process called perspective projection. And we do this usually when you do it with the hardware, you do it vertex based, which is that you look at each vertices of your object, because like I said, we dealing with the graphics primitives, which means we not dealing with every possible geometric object, but with a very small subset of it. And usually in graphics, especially in when you have hardware implementations, the most important and sometimes the only geometric primitive that is supported is a triangle, because a triangle is a very powerful geometric shape that you can create all kinds of other shapes with it. You can even create a circle by using a lot of small triangles and arrange them this way. Now, of course, this doesn't look like a circle, but if you make the triangles extremely small, then this really could look like a circle. And if you can draw better than I can, it really also would look like a round circle. But you get the idea. So this is why we're often dealing just with triangles if we do a hardware-supported graphics. And this process then is called, this is also why this process is often called vertex processing or geometry processing in a more general way. And this process involves the projection of the triangle, the 3D triangle on the 2D screen, but it also involves some sort of shading, for example. So for example, if we know that this is a red triangle, then we're projecting the 3 points from the triangle to the 3 positions they correspond on the screen. But also, if we know that these are red, then we also do the processing of the color. If we already know the lighting conditions, then we also consider that. And then we know that we have 3 red triangles here, and we know how the structure and the material of the triangle is, so we could also draw that later. And also, for example, another thing we have to do, so one of the things we do also in this step is a little shading, but we also do something that is called clipping. So for example, the point is, if you look at the screen, you only see a small fraction of your world. And if, for example, you're making a movie or an interactive game in a huge environment, then you have a model of the whole environment, but you only see a small part of it, which is the part on the field of view from the screen or from your virtual camera that you have here. So if you have, for example, a triangle that is here partly out of the screen, if you would project it on the screen, it would look like this here. But of course, this part you don't have here. So when you want to draw it on the screen, you do not only need to know this point here and these 2 points, but you need to know this point and these 2 points here. So you have to calculate them, and this is usually done in a process called clipping, which is basically taking this part and throwing this part away. We will talk about the techniques about this later, but since you're already using these at part of the practicals, you will run over this term sooner, which is why I want to mention it. Good. So this is the first step in the pipeline, where we go from the 3D geometry to the 2D geometry. But as you see here, we're still talking about a geometry, so we still have an abstract representation of the triangle on our 2D screen. But what we really want is, of course, we want to know for each pixel, do we have to draw this pixel? Is this pixel part of the triangle or not? So what we want to have is, we have an abstract representation, a geometric representation, which for a triangle is just 3 points. And we know if we connect them, we have a triangle. And if we know what color it is, we can draw it. But we have to make the decision, is this pixel, for example, not part of the triangle, and this pixel is part of a triangle? We have to make that decision at some point where we draw it. And this process is the next step in our pipeline, which is called the rasterization, because we're moving from a geometric representation to a raster representation. Good. And so we're moving from a 2D representation to pixels or fragments. Often in this context, the term fragments is used because fragments describes like a little more generalized version of a pixel, because when we do the processing, for example, if we have two triangles and they're in front of each other, then of course we only see the first one. But if we do not do the ray tracing, where we just follow the ray from the observer, where we just hit the first object and we already know this is the first one and this is the only one that we see. But if we do a model-based approach, then we also have to decide, then we're processing also the one behind it, so we have to also decide at some point which of the two we are drawing. So we have two fragments, but then they both represent one pixel. Also, if we have, for example, a transparent triangle, if the first one is transparent, then we also, of course, when we draw the pixel, have to consider the color of the one that is behind it. So we have to consider also that fragment, and this is why we sometimes make this distinction between fragment and geometry. But I also have to warn you here, this is a terminology that I got from the book. In the API that you will use in the practicals, they might use a different terminology, because of course that is always then the specific implementation. But this is the part that you also have to kind of make yourself familiar with it, that you have to learn to be able to switch between different terminologies. Good, yeah, and this is then the processing of the fragments, which I just explained here already, is then called fragment processing, which is the last step in our pipeline, which is then processing the fragments, deciding which is in front, deciding on how exactly they look like. So we do more shading here in this situation, and also then we do something that is called blending, which is then basically combining different fragments into one final pixel. Good. And then of course we have we know for each pixel what color we have to draw there, and then we write that color into the so-called frame buffer, which is basically an array representation of the final buffer, the final information that we put on the screen. Good. That is something I already talked about. Shading can be done at different stages in the pipeline, as we will see. And clipping is something that I also already talked. And like I said, we will talk about this more in detail later. So this is just a rough overview. And this is an overview of the course. That's the current plan. Like I said, small changes may apply, but it should be pretty much the same. And based on that, you can also look up last year if you want to go ahead. You can already see what kind of chapters in the book relate to that, for example. Good. So these 4 or 5 lectures here will pretty much be very heavy on the mathematics side. So next time we will talk about a lot of mathematics. This will be a lot of mathematics. Here we'll talk a little bit about physics, which is then how the lights are, how light is modeled, and the transformations is then the modifications of different models. And this here will then be the midterm exam, which will be somewhere here. And this, oh, of course, this is the old schedule now. So forget about that. The new schedule is online, yeah. So there are some changes, because for the practicals there will be some situations where we'll talk about things where you will see the practicals, and there is some stuff not covered in the lecture yet that will then be covered later. But again, if you want to look ahead, go ahead, just look at the material from last year. Good. Yeah, that's that's last year. Any questions? No. So for those of you who are looking for a teammate for the practicals, who don't know anyone, just go to the practicals now, room BBL 175, and then try to find someone there. All right.